Well, I want to welcome everyone who's watching or listening or reading the second part of this oral history with Ed Feigenbaum. In the first part, we went pretty much chronologically, starting when you were born and ending with the national service that you did after your retirement from Stanford. Now, today, what I want to go through is sort of cross-cutting topics that go, certain themes that happen throughout those years, and it's easier to organize some parts of your life chronologically and other parts by topics. So it's topics today, and the first thing I wanted to it strikes me, if you had to summarize a lot of your career was based on the idea of heuristics and studying heuristics as a great metaphor for doing artificial intelligence research. But what I want to ask you is, what were your own heuristics for the personal choices that you made through your life? So the way it gets through to you and. Yeah. Instead of the scientific, but also the personal.
Don, that's a really good question, and there was a time in my career when I would try to write them down and give students lectures on that as kind of career direction. And those will be, not some, they will all be in the Stanford archives, in the special collection of my stuff. So right now I'm just going to try to spin off a few off the top of my head. Where shall I start? I think I'll start with one that I've talked to you about earlier, which was that I found myself to be a better discoverer than inventor, which meant I needed to pay a lot of attention to empirical data. Because in empirical data, one can discover regularities about the world, which means that my methodology kind of forced me to pay attention really carefully to the real world. So not to move off in fantasy land in science, but to stick pretty close to reality. That was one thing. The other thing was, never move off into a complicated problem area unless you have a problem domain that you can get data from, that you can work very closely with. That led me, I saw it at work when in my graduate training under Simon and working with Newell on their chess playing program, or their work on, even when they were doing GPS, they still were using concrete task domains like trigonometric identities. And then I spent years looking for the right task domain for studying the problems that later became, scientific induction problems that later became the Dendral program. That was a key thing throughout my life, was to look very carefully at the problem areas. Some would be terrible. If you wanted to work on a certain kind of problem, some problem domains would be terrible. Some would be extremely good. Newell, who was always impressed with the Dendral project, but not so much with the brilliance of the ideas in the Dendral project, which he thought were interesting and a good coupling together of other ideas that had been in the field, but with the choice of task domain and the way of exploiting the task domain to get the results. So that's an important heuristic.
Is it easy to give an example of a bad one, of a bad domain?
Yeah. I'll give you one that I really rejected when I was searching for the domain that ended up being mass spectrometry because of Lederberg's suggestion. But a domain that I was looking at for studying induction was to induce the rules of baseball from a long string of specific activities in baseball. It turned out that just didn't feel right. And one of the things that made it not feel right, and there comes another heuristic, is that I've always wanted to, in doing this, work with people who are genuine experts in that domain. And in the baseball thing, it didn't fit. What I was trying to induce was the rules of baseball.
You didn't know Dutch Faring. He was a friend of mine, but you knew Josh Lederberg. Right? I mean, Dutch was Stanford's legendary baseball coach. But,
No, I didn't. Another heuristic that I used was how to put this. I really like to meddle in other people's domains of work. I just find it absolutely fascinating, which means that there are large chunks of computer science itself which I'm not interested in exploring, relative to, say, exploring physics like you and I were talking about, or molecular biology, or chemistry, or some other domain. I mean, I got involved with many domains, X-ray crystallography, engineering domains. I find it fascinating to open the door into those domains, become a rapid expert, not a real expert, just a sort of a 30-day wonder expert in the domain, and find out about a lot of things.
well, is it that you like the idea of finding a pattern in something complicated, taking something that's organic and messy and bringing some order in?
Yeah, I think that's part of it.
If it's already clean, you might not feel attracted to it because you have that you're better off finding out how to deal with the more. I mean, even baseball itself is a good example of something that's that is complicated, lots of nuances to it, but it doesn't have a structure where you want to deduce something about it. So
yeah. I'm not sure that I thought it through that carefully, but I think you're right.
So this is like an experimental physicist has a complicated universe to observe and wants to try to see the patterns in that. Is that right? But
yeah, I think I'm much more like an experimental physicist than I am a theoretical physicist. And a lot of my computer science colleagues, and indeed our students who come from mathematical backgrounds, are much more like theoretical physicists. In fact, I've kind of named a disease that they have, which has gotten popularity because Doug Leonard has used the phrase a lot. It's called physics envy.
Physics envy.
Physics envy. Our friends in computer science have a lot of physics envy.
I see.
And heuristic programming is kind of messy. That's in fact what Polya was trying to tell people back with his books on patterns of plausible inference and how to solve it. Talking to his mathematical colleagues and saying, when you prove a theorem and you get to QED, it's not all that simple. You've done something a lot more messy than that to get there. You've searched a big space. You've discarded lots of avenues in the space. You've used a lot of rules of good guessing to get there. But you just don't want to tell people about the messiness of that. And what I'd like to, so the whole idea of using heuristic methods that was to employ all those armaments, you might say, in the service of pruning these enormous spaces. And
Yeah. Yeah, and computer science has its characteristic of non-uniformity, where a computer program has step 1, step 2, step 3, step 4, while a lot of the pure mathematical things, they have one equation that applies to everything, and you don't have, to a mathematician, the hardest thing is you have a theorem that you have to prove by considering 10 different cases. But in the heuristic kind of work that you're doing, you've got thousands of cases, and still you're interested in finding some paradigms that enable you to deal with these, because they don't just go away. Not everything in the world is uniform. So it's a different, at least I'm sorry, I'm injecting
So,
my own.
yeah.
My own.
Let me give you another example of,
Yeah.
of a heuristic that I was using. And I used it sometimes, and I didn't use it other times, and when I used it, it was successful, and when I didn't, I wasn't so successful. And that is, it takes a while to become really, really good at something. Stick with it. Focus. Persistence on problems is really, not just problems, but a whole research track is really worth it. And switching right in the middle, flitting around from problem to problem isn't such a great idea. The thousands of little intuitions and pieces of the heuristics you gather along the way for dealing with a particular problem area, or your part of computer science, are enormously valuable in making the next step and choosing next steps that don't waste your time and your students' energy and your own energy. Of course, I violated that by doing a lot of miscellaneous things in my career, which defocused from those things, but I enjoyed them and did it anyway.
But you did, yeah. I mean, there are some people who are really good at inventing a theory where it's needed. I'm thinking of Jeff Allman, for example, and then going to another topic a year later and seeing where another area needs a theory, and so but those are very specialized kind of talent. Now, so you started with mass spectrography, the work on mass spectrograms, and then it went into medicine. Did you ever think of? I've always wanted to know if you ever thought of like bubble chamber and cloud chamber, the things which are somewhat analogous, where you have a lot of data.
So there was a particular. The answer is yes, we did, and actually didn't work on that particular problem, but worked on similar ones in medicine. But the reason, the one you mentioned, it was salient, was that SLAC was being built, or had just been built when I got here, and Bill Miller was running the SLAC graphics group, and so we had quite a bit of conversation about that, and it would have been actually a very good problem area. And I'm not exactly sure why we didn't move down in that direction. It's just that I had...
But you never claimed them as artificial intelligence, as if they were also working on AI.
See, I think that the problem, I'm just guessing now, but the problem may have been that the physics of the dispersal of the particles in the bubble chamber or cloud chamber was too well known. It wasn't...
It didn't need more funding or more.
Well, so
more
the
people working on it.
AI field, as Nils Nilsson and others have said over the years, and Roger Schank, kind of breaks down between the neats and the scruffies. And
The what?
the neats and the scruffies.
Neat and scruffy, okay.
McCarthy represents the neats.
Okay.
And over the years, Newell and Simon and Minsky and myself and Schank and others represented the scruffies, where we don't insist on a lot of formal clarity in the models. Well, in the case of the bubble and spark chamber photos, there was just a lot of formal clarity there, period. Mm-hmm. You didn't really need, but in medicine there wasn't, so it was kind of a good area.
Yeah, okay. But there was more of a need for it that you could see in already there were
But I've
there
got
were
to say,
zillion physicists working on it.
but I think that what I just said overstates the case in the following way, that, and again, it's a heuristic in life.
Yeah.
Meet a wonderful collaborator, and in this case it was Joshua Lederberg. Meet a wonderful collaborator and really work with that collaborator on some meaningful problems. Lederberg and I worked on a whole chain of problems, and then even when it wasn't directly in our field, we were involved with that, like in diagnostic medicine, or Josh on the engineering side of what we were doing. That's a valuable heuristic. Another way to put it is that, as we discussed in your oral history, you said you were pretty much of a loner, that you like to work. You gave some examples of where you weren't, but you said most of the time you like to work by yourself. And one of my heuristics is liking to work with a small number of very smart other people, like Carl Geraci or Josh Lederberg, or...
Well, that actually was a good segue to the next thing I wanted to ask you, was different gurus, but I guess it's the word guru isn't right. I mean, you mentioned Herb Simon many times last time, and he was definitely a guru for you. But also, I mean, as an advisor, I found I couldn't work with my own PhD advisor on a same level, you know. Somehow, but with Lederberg, you were more of a team. Is that what you, or would you describe other gurus in your life, or
Yeah, sure.
other?
Sure. Great question, and in fact, in trying to myself structure my past in a reflective way, perhaps in that which might lead to an autobiography, I've thought of structuring it in terms of people. I've worked with, and people who have influenced me, and people I have influenced. I think so. No question that the two biggest influences on the way I think were Herb Simon and Joshua Lederberg. Simon's influence was absolutely fundamental in two things: getting me interested in the breadth of the world's problems and not being too concerned with the formal details of the analysis of it. That's why I said earlier, I think in my last session in the interview, that I thought of AI more as a behavioral science than as a mathematical science. That kind of came from Herb's breadth.
Now, with Josh, did you go to him, or did he come to you?
I'll tell you exactly how it happened. Well, if I had a copy here of the book Computers and Thought, I would read you a paragraph at the end of the introduction to Computers and Thought, which gives you my projection, or my statement about what I thought was the fundamental importance of the problem of induction.
Mm-hmm.
And the more I thought, so I was looking for a problem domain with which to work. It wasn't an intense problem, because I happened to be, at that time, for reasons that are historical, I happened to be teaching in a school of business administration where I didn't have any great graduate students anyway, so it wasn't a pressing problem. But so it took a lot of thought, and in the middle of 1964, I was invited to a series of Saturday morning seminars, workshops, at the Center for Advanced Study in the Behavioral Sciences, which is on the hill behind Stanford. Carl Pribram was running that. Carl was a neuropsychologist who had participated in writing an early book on information processing psychology, what we now would call cognitive science. His book was called Plans and the Structure of Behavior, Miller, Galanter, and Pribram. So Carl was really involved in that field. He was running this workshop on what amounts to models of minds, whether they were artificial minds or natural minds. And Josh had gotten interested, I should say, re-interested in computing. He had been interested in computing at an early stage of his great career. But then he put it aside because he had other things to do in the fabulous work he did that won him the Nobel Prize. But he got back to it in roughly 1964, taking a course from George Forsyth in Algol and using a problem related to organic chemistry as his test domain for testing out his understanding of these Algol ideas. So Josh knew McCarthy. He was interested in the subject, and he showed up at this Saturday meeting, and that's when I met Josh. So as soon as I talked to him about my interests, he immediately had suggestions to make, and one of them was concerning mass spectrometry. He was working on it in relation to putting a planet probe on Mars, looking for signs of life precursor molecules. And the idea of just beaming the data back to Earth for humans to analyze didn't appeal to him.
I see.
Put the software on board and let the planet probe tell you what the structures of the molecules were. So when I got to, that was since '64, when I actually showed up at Stanford, aside from saying hello to Forsyth and McCarthy, the first person I looked up was Lederberg. And the collaboration began almost immediately. He remembered our conversation. I remembered our conversation. It seemed like the right thing to do. We just fell into it.
This was before he had a Nobel Prize?
No, he won the Nobel Prize in 1959,
I see.
I believe it was. And then he gave all of his Nobel Prize speeches and all that, finally got sick of traveling and decided to look for another field to work in, and he got interested in computing and artificial intelligence.
So he won the Nobel Prize, he's in his 20s, 30, and he's
Very
pretty
young,
Yeah.
very young
Okay.
person, yeah.
So you told me a story once about his stack.
Oh, yeah,
is that
so sure, I'll repeat that. Josh, I know if you're listening, this is my interpretation, and you don't have to buy this at all. I just saw Lederberg yesterday in New York, and he said he was interested in hearing this oral history. But I was trying to, let me start this again. One of the questions that I and others had been looking at during the 60s and a little bit later in the 70s, Herb Simon was the leader of this. I was more of an AI engineer, you might say, and he was more of a psychologist. But the question was, what is it that distinguishes experts from novices? Herb did some experiments and came up with some ideas. I was asking the same question of myself when I would watch Josh Lederberg at work. When I would watch his mind at work, or listen to his mind at work. What is it that makes Josh so amazing, so penetrating, so deep, looking into problems? And knowing what I knew about problem solving, I made a conjecture, which is that the portion of Josh's immediate memory which serves as a place to return to subproblems was just a lot bigger and more efficient than the rest of us. He could keep a deeper stack of it. Maybe I should say it another way for the people watching this oral history. One of the key techniques that AI people, the models that AI people use of problem solving is what's called subproblem reduction. You divide and conquer. You don't solve a big problem all at once. You solve it by dividing it up into subproblems, which you divide into subproblems, and you have to keep track of that whole chain of what we call the subproblem hierarchy. And Josh just had an amazing way of keeping track of where he was in a deep line of thought. Mm-hmm. And my feeling is that can be as genetic as any other thing. It can be as, I mean, I don't think of myself as being able to run a 100-yard dash fast or a 4-minute mile or anything like that, because I don't have the musculature to do that. Mm-hmm. There's some things that are just genetic, and maybe Josh's deep stack is something that's genetic, or maybe he figured out how to train himself to do that when he was young.
No, I was thinking, it came up in the other interview too, where we're talking about levels of abstraction, and it's very similar. that you have to know the state of lots of different things at different levels. That's
Don, it's another thing that comes up, you mentioned it in your interviews, is the level of concentration you need to do that. You
Yeah.
can't be interspersing other symbols with that stack
yeah.
when you're doing it.
Yeah.
It's too hard to do both at the same time. I guess the lesson for kids out there watching this interview is don't listen to a lot of music while you're doing complicated things, because those are just other symbols which are coming in there and bothering your stack.
Yeah, right. You can listen to baseball games, though, sometimes it helps. And I'm just kidding. But since baseball came up, when you're doing something boring, some kind of distractions do help. But when you're doing the science, the interruptions are killers.
Killers,
Because they
right,
destroy the-
absolutely.
Yeah.
Yeah, and so therefore you find people like, people who take deanships saying, one of our former deans at Stanford said, I remember when he took the deanship, yeah, that's okay, I can do that part-time and the rest I'll run my laboratory.
Yeah.
Well, there's no way you can run your laboratory when you're doing that. You just lose it.
Yeah, okay. Now, so, any other gurus or?
Yeah, I think, so Geraci was another one. Geraci, the way Josh and I got Geraci involved, so let me tell you a little bit about Carl Geraci. He's a brilliant person. Lederberg once called him when I heard Lederberg call him a phenomenon of nature.
Well, I was once having lunch with Josh, and I remember exclaiming, Josh, how could you have ever evolved? Okay, but.
Yeah, right. Remind me to come back to that question, that
okay.
exact thing you just said.
Okay.
Because I want to make a comment about that.
Okay.
That's another heuristic, actually, of my life and career. But anyway, Geraci was the so-called father of the birth control pill.
Yep.
He then went on to run Syntex Corporation. Actually, his whole career at Stanford was spent 50% being a professor, 50% running a company like Syntex or one of his later companies at Stanford. He was a collector of, one of the world's great collectors of Paul Klee paintings, and just a very broad intellect. But when we got to know him, he was a mass spectrometrist, one of the best. And he had a laboratory over in the chemistry building. And Josh said, by 1996 somewhere, like 1 year into our project, Josh said, look, Ed, we're running out of what I know about mass spectrometry. So in order to make any progress, we're going to have to get someone who really knows this. Let's get Carl. So the trick, we had a little strategy, which worked. We took Carl up to the Stanford AI lab where our program was running under time sharing on McCarthy's machine. And we showed him the program working on, well, first we showed him the good stuff, which was working on some amino acids spectra. And then we showed him the program running on alcohol spectra. And it was doing a terrible job, even though alcohols are much simpler. But it didn't know anything about alcohol mass spectrometry. So it was doing a terrible job. And Carl said, that's terrible. And we said, yeah, that's right, Carl. Now, what is it that you know about alcohols that our program doesn't know? And that got Carl hooked. And from then on in, it was just Carl and his team supplying that kind of knowledge. And then we had a program of research that Carl laid out that extended the range of Dendrol's abilities. Each time that we went into something more complicated, we had to do more complicated stuff in the program. Like at one point we went into ring structures, which means that we had to get Harold Brown in he came from Ohio State to help, and some other people, Larry Mazinter, to help figure out the, and we consulted with you and we consulted with Bob Targent about understanding the graph theory of the ring structures and getting that into a program. So Carl was a big influence on what we did. Then I would say another influence, it was a person I influenced a great deal, but he also influenced me a great deal, and that was Bruce Buchanan.
I was just,
Bruce-
guessing that was
I
going to be.
found Bruce, luckily, stroke of sheer luck. Bruce was a graduate student in philosophy of science at Michigan State. He applied for a summer job at Rand. I was working in the summers at Rand at that point. Paul Armour, who was hiring people, gave me this application and said, Ed, would you like this person for the summer? And it was just when I was thinking about scientific induction. The reason being that Josh's comments had turned me in that direction, that scientists were, it was just a natural to use scientists to study induction because they were professional inducers. That was their job, to look at a lot of data and construct hypotheses and theories. So Bruce came along with this thesis he was writing called Logics of Scientific Discovery. Listen to those words, logics of scientific discovery. That was exactly, I mean, it couldn't have been more tailor-made. So Bruce came in the summer, and then when he wanted to get a job as an assistant professor of philosophy somewhere, he asked me to write a letter for him, and I just said, Bruce, you don't want to do that. What you want to do is come and work with us. And I told him what the project was, and he did. And over the years, it was a really great collaboration. Bruce had just the right flavor of insight from his background in philosophy and his work in computer science to contribute to our work. So that was excellent.
Is there, I don't know how to ask this so that you can answer modestly, but other people who would put you on their list of gurus?
Yeah, so I think, yes, the answer is, and a lot of them showed up at the 70th
Right.
birthday fest.
Yeah, that we
It
had.
wasn't kind of a shrift, it was
Yeah.
just fest.
Well, yeah, we call
But
it.
Doug Leonard is one of them.
Yeah,
His graduate student career was kind of languishing under Cordell Green. It wasn't getting anywhere, and he somehow discovered me and described what he wanted to do. It fit exactly what we wanted to do. He just went straight ahead. That was his AM
the AM
thesis.
yeah.
And we've had a very good collaboration over the years. Another one is Randy Davis.
Randy Davis. Mhm.
With Randy's work on
Yeah.
explanation.
Yeah, I see. And
I mean, I don't know exactly who would
I don't know, Peter.
but
Friedland?
there are many.
What, I'm thinking Peter Friedland maybe, or
Oh, Peter as well. Sure, sure. Peter and Mark Stefik did wonderful theses. Well, there's a whole story there about the so-called Malgen project, molecular genetics. It was the first project in which computer science methods were applied to what is now called computational molecular biology. And the reason we were able to get in there early is that we had Joshua Lederberg as our collaborator. The genetic engineering methods had just been invented by Stan Cohen and Herb Boyer, and Stan Cohen was one of the co-PIs of one of the projects in our lab, of the Meissen project. And so we were there very early, and we also we were masters of a computer language that was way better at handling symbols than it was at handling numbers, namely Lisp. So, but that's what their domain
That's
was.
what they-
It was all symbols. So we were able to give them tools, they were able to give us insights. And Peter and Mark did the first two theses on using AI methods for experiment planning in molecular biology.
yeah, you had the vocabulary and the kind of theory that was needed to talk about this kind of modeling.
Yeah.
Yeah.
That's right.
What about, okay, I'm thinking Doug Rutlag, was he involved with this? Maybe I was
Wait,
wrong.
say it louder.
Rutlag.
Oh, Doug Rutlag. Okay, so here we were working in molecular genetics, molecular biology, and we had Josh, but Josh was at that time getting to be quite a public figure, writing columns for the Washington Post, and eventually 2 years later becoming president of Rockefeller University. And we needed a more hands-on molecular biologist who was able to work with us on a day-to-day basis. So we recruited two of them with help from others. I don't know who helped us get them, but Doug Brutlag was one of them. He was in Paul Berg's department in molecular biology. And Larry Keddes in the medical school, Keddes, was a hematologist who was interested in molecular genetics at the time and was really interested in computational methods. So Doug and Larry were our domain experts, and Peter and Mark were the AI students, and I was kind of the AI and computer science glue for all of that. Then later on, when the product of our work turned out to have a very broad applicability because the field was exploding late in the 70s, exploding from a few people to hundreds of people who were interested in doing this. The software got to be very widespread. First on a NIH-supported time-sharing machine at the medical school, and connected to what was then the ARPANET, and later in the basis of a company called IntelliGenetics that was started by myself and Peter and Doug and Larry.
I want to go into companies later, but
Yeah.
right. But I guess now would be a good time to just ask about SumX and Acme.
Yeah, good point. In fact, Josh and I yesterday were just talking about the history of all that. Okay, so in 1965, there was a confluence of events in computing occurring, besides the formation of the computer science department, which occupied the mind of George Forsyth very much in early 1965. There was a confluence of other computing events going on. Basically, a new generation of computing was arriving on the scene in the form of either the IBM 360 set of machines, for some people, or the CDC 6400, 6600 set of machines. And even at the time, the original PDP-6 was showing up at that time. It wasn't as powerful as some of those other machines, but it was a very flexible, beautiful architecture machine.
This was the first, well, I don't know, Silicon Revolution or some way. I mean,
Yeah,
the
that's right.
transistor.
Yeah. Solid logic is what IBM called it.
Yeah, solid state, yeah.
So it was time to augment the computing capacity of the Stanford Computer Center. It had a Burroughs machine. It was going to get something else. I mean, it could maybe get another Burroughs machine, or it could get something else. And George didn't want to handle that. He had his hands full with the computer science department. So he asked me if I wanted to basically run the computer center and handle that. But it turned out that Bill Miller had arrived at Stanford, same day I arrived, January 1st, 1965, as another faculty member in our department. And Bill needed to do the same thing for the SLAC. He was brought in to do that for SLAC. And they needed a massive machine. So it looked like we ought to do whatever we did together, because software was a big cost, software was a big pain in the mind, pain in the neck, and we better do it together, and we can master one operating system and not two different ones. Well, so we decided to do that, and then Josh Lederberg had the idea that he wanted to bring computing to the medical school, and why didn't we, A, go out and get some money to do that from NIH, and B, join it in with this other plan. So that's just what we did. We had a plan to, it ended up, I won't go through the gory details of how we ended up this way, but it ended up being a 360 mid-sized machine, originally slated to be a Model 67, but that was never delivered, so it was a Model 65. A Model 91 for SLAC, which was a very fast machine, and a Model 50 for the medical school machine, picked partly because it fit our budget, but partly because it was a machine that IBM was selling a, would you believe this? I don't know exactly what they called it, but my word would be a mega memory. Namely, you could buy 1 megabyte of memory. amazing. 1 megabyte.
Yeah.
You could get 1 megabyte of main memory, which means you could write a memory-based time-sharing system without a lot of swapping.
Yeah.
If you kept, imagine you had 1 megabyte to do it
I
in.
can't imagine. I had, 10K for.
Yeah, right. Exactly.
Yeah.
So we bought a 360/50 with this big memory, so-called big memory. And on that, and I hired a friend of mine from Berkeley, Geo Wiederhold, to run that facility and develop that time-sharing system. That was called the ACME system.
Okay.
I think it was ACME stood for I'm not positive of this, but it was something like a computer for medical education or something like that.
Wonderful, okay.
Something like that. And then,
And that was different from SumX.
now, okay, ACME, so ACME was a time-sharing system for the medical school, not just for our AI research. It was
Okay.
in
Right.
fact, for our AI research, it wasn't all that good because it didn't have well-developed Lisps on it.
Right.
And so we were using McCarthy's ARPA-supported PDP-6 and the
PDP-6.
PDP-10. But then our projects really grew up. Dendral was very successful. We moved into medical diagnosis and a couple other medical-related projects. So it looked like it was time for us to get, basically for us to do what McCarthy had done up at his lab, but to do it for our own lab. We were on campus, not up in the foothills. Partly, largely actually, because we were collaborating with experts on campus, and driving up to that facility was a big pain. We needed them when we needed them. We didn't.
Right.
It took a half hour to get around campus and up on Arastadero Road to. So we. So Josh and I applied for some money from NIH for a machine like McCarthy's, but using the 10x operating system rather than the one that they were using at Sale. Let me talk about Licklider a minute.
Good, yeah.
Licklider had come back to DARPA for his second time around. He was the guy who sponsored McCarthy in the first place at Stanford and sponsored me at Berkeley in the first place. But he had come back to DARPA for a second round, and Josh and I, and of course we had been involved, my group had been involved with DARPA PI meetings and the growth of the ARPANET at the beginning, and we asked Licklider if we could attach a non-DoD machine to the ARPANET, namely an NIH-sponsored machine.
Mm-hmm.
And he said, of course. So we got ourselves an IMP, I believe it was at the time, and attached ourselves to the ARPANET. And that suddenly...
What year are we talking about?
Like roughly 1973.
Oh, okay, so this is...
Something like that.
I see, so...
Licklider came back in 73, I think.
Oh, okay. So then, was this the only non-DoD machine at the time?
At the time, it was the only non-DoD machine. But that suddenly opened up the prospect that the stuff we were doing, to be more specific, the software we were developing in our group could be made easily available to a national community of researchers wanting to do AI in medicine. That became the acronym AIM. AI in medicine was the national group.
Oh.
SumX was...
SumX-AIM.
Yeah, and SumX was the Stanford University Medical Experimental System, dash, AIM, the Artificial Intelligence in Medicine National Group.
Do you remember what the internet would, I mean, how many different operating systems were there? You say you have 10x on this one, and McCarthy had his, I don't know what it was.
Homebrew.
Homebrew weights, and then there was ITS at MIT, the Internet Incompatible Timesharing.
Yeah.
I suppose there were quite a few different ones then.
Yeah,
Okay,
maybe every machine had it.
Yeah, okay.
No, 10x was, eventually 10x kind of took over on the DEC machines, but...
Yeah, but anyway.
Anyway.
It's good that the internet actually started in this, with all these different kinds of machines, because that made it more likely that it would be useful in the future.
Well, and I think they had that in mind from the very beginning.
Yeah. Okay.
So then we hired Tom Rentfly from Caltech, a real expert who just ran that facility for us, did a superb job over a 20-year period.
And was this used by people all over the country then?
all over the country. In fact, when I was the software I was telling you about before for Malgen, when we provided a tool for sequence analysis, which is now common. Now it's everybody does sequence analysis, but it was just us and a little biology group in Wisconsin, I think, that had developed software for it. We had 300 users of that coming in over tips, not imps, but coming in over tips located all around the country. Remember, ARPA had put in modems on computers called tips.
Right.
So we had a big user community.
And imps. Yeah, it's like I was using Maxima at MIT at that time. So it was a similar thing. People from MIT would log into SumX, or people from Wisconsin. So,
Yeah.
Right, okay, good.
Well, or
Yeah.
Saul Ameral's group at
Right.
Rutgers
Yeah.
was another example, Carnegie Mellon
Yeah.
people.
Okay, good. Now, let's see, going, I don't know if I should try to go smoothly through all these topics, or, yeah, let's talk about companies now.
Wait, Don, can I just back up a second and say one more thing about SumX?
Yeah,
SumX is in danger of being sort of bypassed by history. In the sense that Tom, who is now retired, I don't think he's had an oral history here, and I don't think the history of SumX has been written, but someone ought to go back and do it. There are some absolutely brilliant things that happened at this medical computer facility. For example, the Computer History Museum shortly will have an exhibit in which they're exhibiting the history of the first router that was done at SumX. And it wasn't done by Cisco. No matter what Cisco, the founders of Cisco claim, that stuff was taken from what Bill Yeager did. And the Computer History Museum is cleaning up that piece of history. But there's a lot of other stuff that someone ought to go back and do that history sometime.
so the archives from McCarthy's computer, all the DART tapes, all the backup tapes have been preserved. Is there a similar thing for SumX, for people
yes
to
and
actually
no.
look at the data?
Tom Rentfly saved 1,300 dump tapes when SumX went out of existence. And he saved 2 tape readers. And he's using a PC-based simulator of what the machine used to be. But on the other hand, Tom's pretty busy doing other things. So there's no
It hasn't been
There's
lost
no
yet.
group, there's no volunteer group that's helping Tom preserve the history of SumX. He did give Lederberg and me what amounts to the email of SumX from the time we got online to about 1980, 1979.
Email, okay, yeah.
But then there's all the files in the directories, and there's a whole history there.
Yeah, well, this is, I guess I guess I should talk a little bit about history then, since we're in that. I'm trying to segue through my question.
Yeah, sure.
And so you should show everybody the tie you're wearing. It's a core memory tie.
Yeah.
So, I don't know if it's possible to zoom in on that. But tell me
It's
the
from
story.
the Computer History Museum, actually from the Computer Museum in Boston.
Yeah.
Gwen and Gordon Bell gave me this tie once, and it's a representation on the tie of the wires and the cores that used to go into core memory.
I just wanted to, I mean, in general, you've got this great interest in history and preservation, and I wondered if this is late in life, or if you had this all the way through, or if you were, if you loved history when you were younger, the same as you do now. What are your thoughts about these things? I know there's also talk about semantic web, which we can get into too.
Yeah.
Okay.
When I was younger, I was too busy for history and not cognizant of the importance of it. I hadn't lived long enough to understand the importance of it. Even though history as a subject was okay, it wasn't, I mean, there's nothing I disliked about it, but it wasn't like I had this lust to be a historian and accidentally ended up a computer scientist. But after I interacted with Josh Lederberg for several years, he taught me the importance and value of saving documents and annotating them and putting metadata on them, making sure they were organized and they were sure to be valuable someday. And I began to understand that myself as I saw ideas unfolding and influences on those ideas unfolding. And as I got older and began to see my own career unfolding and began to realize the impact of the ideas of others on my ideas. So I became more and more of a historical buff. Then Lederberg and the National Library of Medicine collaborated on the first of what became a series of websites on the National Library of Medicine computer called Profiles of Science. And that convinced me to get very serious about, well, I was semi-serious about the archives. I spent a lot of time on the Feigenbaum archives in 1985 with Henry Lowood and setting up this collection at Stanford. But more recently did a second accession and became interested in the digitization of them, the organization of that digitization so that it would be meaningful to historians, curators, scholars 50 and 100 years from now who were interested in the flow of ideas around this time. I mean, look how many people are interested in the flow of ideas around Newton's time, Newton and Leibniz and the calculus. And
I was reading last night about Darwin. I suppose I don't know. It's not as well known as it should be, but he was in poor health throughout most of his life, and he referred to this all the time in letters that he wrote and so on, So there's a wonderful article that just came out by two doctors in Chile diagnosing his medical problems, but it also fits in with all of his life very perfectly, and without this kind of documentation, so much bad conjectures would be flourishing, and now we know a lot more about the way important things were discovered because of
So Don, another way to look at it would be to say that to go back to the very first question you asked me today, if you're interested in discoveries and the history of ideas and how to manufacture ideas by computer, you've got to treat this as data. This is data. This is fundamental data. How did people think about what was out in the environment? What alternatives were being considered? Why was the movement from one idea to another idea seen as preposterous at one time and accepted at another time?
And you're working now on some kind of facilitating automatic processing of this data.
Yeah, I'll tell you about it a little bit, but I always like to talk about things that have been done and are, someone can, in the future I want one of these scholars to be able to say, yes, he talked about that and here's the program, or here's a representation of it. This is just a conjecture. We're working with the Stanford Library, I am working with the Stanford Library, on trying to do at least a semi-automatization or at least a very significant facilitation of the kind of work that the National Library of Medicine did with Lederberg to create this superb historical digitized website. And I'd like to, and what do I mean specifically by it? I mean that everyone who is a professor emeritus, we're going to start with computer science because that's closest into what I know about, but and I'm going to hopefully get McCarthy involved with it, and maybe yourself, other people in computer science, but I'd like to be able to do it in other fields as well. To give every professor emeritus a kind of a workstation, a history workstation, where they have a computer and some software and a scanner and the help of a library archivist to get them started with metadata and get them started with layering on some additional concepts from their field, which the buzzword in AI, which I don't like, is really ontology, but lay on some ontology things, and then maybe a graduate student or two will add some inference methods on top of that and be able to allow a scholar to draw conclusions from what's in the digital archive, as well as just gather data from the digital archive.
Yeah, we have to find a graduate student who also appreciates history at that point in their
No,
life.
this has been a hard problem. We've been looking around. We finally found an undergraduate at computer science who's doing a minor in history, but it's going to be just as hard as finding a graduate student who is interested in chemistry.
Well, it turned out that last year was the 300th anniversary of Leonard Oiler's life, and 2 graduate students at Dartmouth got the history bug, and they went through and they have set up a website now, but they digitized, 880 Euler's 880 papers and his correspondence in there, and they wrote a description of how they just love this work. So once you can get them started on it, there's hope, I think.
Now, can you imagine what that would be like if Euler were alive,
Yeah.
and you could actually get audio clips from what Euler thought about some of those documents and how he got these ideas and who influenced him? And
Well, of course, he's one of my heroes, and I'm afraid that I don't want to be disappointed either. But,
well, yeah, that's like Newton. Newton wasn't a real good guy. But
yeah, no, apparently he smoked like a chimney. Okay, so, okay, great. I think we can only hope that people who are watching this now will see that they should also do the same then for the history of their time as we're trying to do now with the new tools that'll be available by then. Now, I guess I really want to ask us the most cross-cutting question of all. I might as well get to it now. Is sort of what things make you the most happy? This is a hard one, but just if you had to, if you sort of look at your whole life and saying, these were the happiest times. So what are the?
yeah,
I don't like top 10 questions usually, but
Yeah.
What does this trigger in your
Yeah.
mind when I ask them?
Great question. Great question. So, I don't know if I'll get the order exactly right, and if I
No.
don't, I'll edit it in
Edit
the
it later.
transcript. But
Right.
the number one thing of all is my wife, Penny. It's a wonderful person to be with. The period of time after we met and got married was one of the most productive times in my life, because it was one of the most bubbly, happy times, and it's sort of continued that way throughout life. So that is the number one thing that makes me happy.
Mm-hmm.
And the number two thing that makes me happy are those 4 wonderful girls we have, and now all the grandchildren coming, and they're terrific, and we love to, the girls all turned out to be wonderful and productive and happy, and you know what?
Okay.
I hate to tell this story in a world in which lots of bad things happen to people, but none of those happen to us, and we get together routinely as a family. Not all the time, but at least once a year we all get together, and then subsets, and that made me very happy. Has made me very happy, and continues to make me very happy. Third thing is relationships with a small number of superb people that I've had that continue on. Herb Simon is dead now, but right up until, I didn't know Herb was dying at the time. He didn't tell me that he had a cancer and he was dying, but I would go routinely to Pittsburgh to see Herb. Up until the very end, when Al Newell died, I was in close contact with Alan. Yesterday, I happened to be on the East Coast this week, and it was essential that, in my mind, that I go and see Josh Lederberg at his place. He's not feeling so well these days, and I went and we talked a lot about not only the past, but also is there anything we could still do together? Those things are very, and not just with older people too, like getting together with Doug Leonard is always a great pleasure for me, or Mark Stefik, or Peter Friedland, or people like that, Randy, Ted Shortliff, Bruce Buchanan I see fairly often because I make a point of it. I really want to see Bruce. So that makes me happy. Then another thing that makes me happy is, I mean, those are the people things, and the people things are more important than the...
That's right, but we can talk about different orthogonal dimensions.
Yeah, and so the other thing is...
it doesn't have to be a linear order.
Yeah, maybe it's not a linear order, but it makes me very happy to have the feeling that I got to understand very well and could explain a very hard problem, which is the problem of what is it that makes something or someone intelligent. And I don't understand everything about it, nor does anyone else in AI, nor have they ever, but they will eventually. But I know enough about it now to feel very good about where we got to in that. And so that means that it wasn't all dribs and drabs, and it wasn't all a waste. And it means that I have some ways of answering the question what to do next, because things have worked out in the past, and therefore it's a reasonable extrapolation that if you follow that track, it will work out in the future. So I like that. That makes me very happy.
Okay, so you in other words, you gained some answers to questions that you were trying to look at, and in the process you also gained many friends and who shared the journey and so on.
Wait, John, Don, I wanted to mention one other thing. Two other things. Number one, I never gave up this idea of wanting to plow into somebody else's field. And so the physics you and I were talking about today, that's another example, where it's just a hobby of wanting to find out what the latest is in quantum cosmology and in theories of gravity and so on. And then finally, and not just that, but it's sort of everywhere. I took along with me on this trip to New York, I took along Lee Smolin's book, The Trouble with Physics, which is a very well-reasoned examination of what's going on there. And I also took along Shakespeare's Henry VI, Part 1. That's the kind of... And then the last thing is my music. Singing with the Stanford Chorus is just... When I do it, there's nothing in the world that's making me happier than that.
Right. That was one of the things on my list, and I know you've done this for a long time. Can you say? You were. I know you might have introduced me to Harold Schmidt ages ago, but so you've been with the Stanford Chorus maybe from the '60s or.
Well, so in 1970. In the late '60s, I tried to look for other things to do besides doing the normal thing I would do. The nerdy thing of taking homework with me at night and finishing it up and preparing for my class and going back and teaching it the next day. I wanted to do other things. And one day I saw an ad in the Stanford Daily, student newspaper, for those of you who are 50 years from now watching this. Basses and tenors needed for Beethoven's Ninth Symphony. Well, Stanford Chorus, Harold Schmidt, conductor. I didn't know anything about singing, but I knew Beethoven's Ninth inside and out. I knew it almost by heart, just having listened to a lot of class, listened to it a lot. So I went over to Harold Schmidt and said I wanted to do, here's the ad, and I wanted to do it, but if he auditioned me, I'd never make it because I had no experience in singing. He said, okay, just go sit in the back of the room and see how it goes. That was 1970, and I've never left. Still in the back, still there, still doing things with the Stanford Chorus. Beethoven's Ninth, of course, was done many times, and I even sought out performing it twice with Japanese choruses in 2005 when they do a lot of Beethoven's Ninth in the month of December, which they treat like we treat Handel's Messiah.
Yeah.
And I sang that, and we do routinely. I don't do 3 things a year anymore at Stanford, but usually 1 thing a year at Stanford, and then I find things elsewhere. Like next year, Stanford's going to take the chorus to Beijing to sing Carmina Burana at a music festival preceding the Olympics. Or I joined up with the Berkshire Festival Chorus and sang Rossini Stabat Mater and a Puccini Mass at Canterbury Cathedral, or singing the Verdi Requiem with the Stanford Orchestra and Australian choruses in the Sydney Opera House, just for kicks, and it makes me feel wonderful.
That's good. That's great. Another thing, I remember one time you came to my house and we had we sang Schubert lieders. I mean, Harold Schmidt was there, and I played the piano. Okay, so now another thing I wanted to bring out is that you've always liked gadgets, as far as I know. You were the first on your block to get stuff, and I mean when we talked when I was working on a little 8-bit computer in 1980. You said, you've been playing around with I don't know, Altairs or whatever, things like this, and this is fun again to program this way. And I mean, you were the first person I knew to have a CB radio, and you were Fig Tree was your moniker, as I recall, and so on. You have a Bluetooth hearing aid now. So has this been through your life, and is this a cross-cutting thing, would you say?
So it's getting worse, Don.
Yeah.
Now that I'm retired and I have a lot more time than I had before, I'm getting geekier and geekier.
Yeah.
So I get to, for example, I shouldn't be diving down into the details of the Mac operating system, but I'm using a lot of Macs. My wife is using Macs, and things happen, and you just got to know about them. And
so I can call on you the next time I have.
well, if you have a Mac.
Yeah,
but
I have 2 of them.
I should be hiring someone to do this, but I love the geekiness of it, and part of it is back to when I was. It feels like I'm 9 years old and 10 years old again, and proving Euclidean theorems in Euclidean geometry, where it just felt so good to finally find the answer. You didn't know what you were doing, and then you kind of figured it out, and then you prove the theorem, and it works, and getting back involved with details of computing has that 9 and 10-year-old feeling about it. It really feels good to kind of figure it all out.
Do you think that we're hiding too much of that from people now? I mean, the kids don't have a chance to do this as much as you and I did when we were young. Maybe not.
I'm not sure about that, because we may be hiding that level of it in computing, but everywhere you turn, the levels are showing up somewhere else. Like they may have the same problem they may have geeky issues with their music, digital music that they generate, and the MIDI channels and all that.
I'm sort of reacting to. Yesterday, I was reading the abstracts of a lot of new books that have just come out, and they all seem to be how to use somebody else's library of routines, and how to learn this language or this other one, and reuse software instead of write your own software, and so on. And it's certainly important to be able to reuse stuff, but it seems to be that if your whole life is just to be reusing, it's not much of a life. I'm reacting a little bit to trying to think of how to put more fun into what computer scientists, people who are hired now as specialists in information theory are supposed to do. or I guess developers is another word for it. And it seems that that you can't do the geeky stuff as well, but I'm not sure if you have any similar.
Well, I just think there may be some combinatorics here. That is, what we're doing is packaging up things at this level and saying, these are tools for you to use for being creative at the next level and the next level up.
Okay.
And maybe they are being that creative and we don't know it because we're
Okay.
in our 60s and 70s.
Yep, this is true. I can feel myself getting grumpier by the moment. I mean, good. Now,
Don, I just want to make one comment, though, that is another heuristic that from what you just said. And I know you feel strongly about this because I saw it when you were doing tech and Metafont. People pay way too little attention to the user interface. They're too geeky in the details, and they're not paying enough attention to the human use of these tools and how to make it beautiful. Beautiful is wonderful. And when you see something ugly, it's really offensive. And a lot of the software interfaces that people use are just truly ugly. And I don't know how you can get this across to computer science people. We try a little bit in our department, but we just can't get it across. And maybe it needs something like David Kelly's new Design Institute to do it.
but you use a Macintosh,
Yeah.
which is not ugly. I mean, you presumably enjoy
It's good,
to a
not
certain
excellent.
extent. Yeah, okay. I mean, I like,
I mean, there are serious issues with it, and
Yeah.
I'm sure that they know it.
yeah,
But at least they attend to those issues. And maybe they get 80% of them right, but what do you do when people don't even attend to the issues? Like if you're Sony. Sony has the ugliest engineering interfaces to their beautiful products.
okay. Yeah, the
let-
products are, I see. It's a wonderful artifact, but then inside of it, it's a mess.
Well, for example, Walter Mossberg, for you people 50 years from now, 100 years from now, you won't know Walter Mossberg, but he's the personal technology reviewer for the Wall Street Journal. And he wrote a column on Sony's answer to the iPod, which was actually a beautiful little hardware device. It was an elegant device. But after he goes through and tells you how elegant it is, he says, don't buy this. And the reason is, and then he has these 3 words, Sony's software stinks.
Okay.
And that's the problem, that engineers don't understand what beauty means in an interface.
It's certainly a much underappreciated talent, yeah. You asked me to come back to when I said, Josh, how could he have evolved? And so I better get that off my stack. In other words,
Yeah, okay, so here's the thing I wanted to say. So for the audience, this kind of discussion can get a little tedious and rambling, but this part isn't. This, what I have said what I feel personally, and I've said in public several times, is that there are certain major mysteries, or put it another way, magnificent, superb open questions of the greatest import. And some of the things we study aren't. I mean, if you're studying the structure of databases, that's not one of the big, magnificent questions that I'm talking about. I'm talking about the questions in cosmology, about the Big Bang. I'm talking about the initiation and development of life. But equally mysterious is the arrival or the emergence of intelligence at all. I mean, Stephen Hawking once asked, why does the universe even bother to exist? And you can ask the same question about intelligence. Why does intelligence even bother to exist? the world would go on just as well without us being here, watching it, processing it, understanding it. So why does it exist? And then how did it get to be there? From what did it come? And then how does it work? Now that it does exist and we have wonderful examples, fortunately, we don't have to invent it. We can just, it's all around us. How does it work? Those are the really magnificent questions. And one of them is the evolution of the intellect. And that's when I said, please ask me that again. I wanted to get to this superb, great question. It's why I try to get students to go into AI, because it's or cognitive science. It's a vector into that question. And if they wanted to go into cosmology, I would move them off in that direction too. That's another set of wonderful questions. That's why I go to hear talks by, say, Andre Linda in the physics department at Stanford, because I think those are also great questions.
Good. Okay. Now let's see. Trying to. Well, I guess one of the things it was actually one of the first questions I wanted to ask. I just was waiting for the right moment. But you've accomplished so much over the years. How do you organize your time? Every day. How do you, you wake up and you working on one thing at a time? Or do you shut your door sometimes? Are you on the phone all the time? You work in interrupt mode? How do you go through? Or is Monday different from Tuesday?
Yeah.
What kind of scheduling algorithm do you use in your life?
So what I'm doing now in retirement is a lot different than what I did during the major portion of my career, whereas I was a lot more organized about when I did what I did and the concentration I would put into certain things. Right now it's more like a combination of demand-driven and personal interest-driven. Like, damn it, if I'm right in the middle of this Lee Smolin book on the trouble with physics, and I'm right at a great point, I'm going to continue doing that, no matter. Well, if I'm coming down to the Computer History Museum to talk to Don Knuth, I'm going to do that. But otherwise, I'm going to sit there and read that book.
Okay.
Or if I get tired of reading about physics, I'll switch over to the Shakespeare, or whatever. But so it's more like personal attention driven.
So you have a reservoir of a few things that are currently, but you're always working on something.
Yeah, I'm always working on something.
I mean, you don't have too many things on the calendar now as you used to, but you do of course have rehearsals.
Well, the great thing about being retired is not that you work less hard, because what you do is it's kind of interdirected. You always want to. The world has so many things you want to know before you're out of here that you have a lot to do, but it's more like no one else gets to put something on your calendar. That's what I really like. I get to put the things on my calendar.
So, but let's go back then, 20, 30 years, how did you work it then? Was somebody else keeping a calendar for you?
Yeah, always.
And so would you have a leisurely breakfast? You'd come into work and you would say, now what am I supposed to do? And every 5 minutes somebody else comes in the office? Or did you have special days? Did you reserve some blocks of time where you could get certain kinds of work done? I'm just curious.
The honest truth is, now that you're asking me this, I've never really analyzed it deeply. But I would say that there was there were blocks of time allocated to what I would call intelligent delegating. That is, if you wanted to get something done in a laboratory, you wanted to make sure the person understood what needed to be done, and if you weren't quite sure, you would work it out with them, and then they would go away knowing the kind of thing they should do. And that takes time. You can't just, and then you have to get them, you've got to get them motivated to do it anyway. So that was part of the time, setting aside blocks of time for that. Another setting aside blocks of time was for intellectual interaction. Like, I just would be more creative when I met with Bruce and Josh together and some of our people. And we were bouncing ideas off the wall, and Josh would come up with 100 different ideas, and 99 of them wouldn't be right, and one of them would be brilliant, and just kind of working that out. So that was blocks of time. And then there was just blocks of time to do. Young people don't understand that life consists of a lot of stuff you just have to do that isn't all that much fun, but you just have to do it. And so you just have to sit down and do stuff like that, like when you're department chairman, or when you're running the computer center, or when you're Air Force chief scientist or something like that. They're just things you have to do.
Yeah, I guess I often sort of schedule the thing that I most dread to do, but I'll be happiest when I finish, provided I'm ready for it. The hardest thing that I'm ready to do, because in a way, because then I can get stuff out the door. Because there's always stuff that isn't so much fun, but if you keep postponing it, it gets worse. On the other hand, if you look at it from the wrong point of view, you say, well, then I'm never having any fun. Because
yeah, I know, that is the big problem. And one more thing I think about the allocation of time is that I tend to allocate far more time than I notice my colleagues allocating to other people. That is, making sure that I really like other people. I really like the people in our department. I really like the administrative personnel in our department. I just want to keep touch with them. And even if there's nothing really to talk about, just go in and say hello and be friendly. And that I just devote more time to that than other people do. So, it's not like I program the time. It's not like I say that tomorrow morning at 9 o'clock I'm going to go in and talk to Peach Turner.
Of course,
it's
right.
just that I just do it.